Okay, so I'm going to show you a little more on vectors and stuff. I'm going to use a little simulation thing in order to show you a couple things. So first things first here, I'm just going to crack a little vector here. And it shows like the magnitude and direction. A couple of things here. First of all, it's really common when you have vectors, for vector notation, is to put like a little arrow on top of it. So example, this would be a velocity vector. So if it was just a v, that would be speed. But since it's got a little arrow on top, it tells you its velocity, and the length is 12. And as you can see, this we're talking before, the longer it is, the greater the magnitude and stuff like that. Now there's also the angle, and there's the angle right there. And you can see it's measured from like the little positive x-axis, and then it goes up to where it actually is. And these are all positive angles, and then what this simulation does is as soon as it gets past 180, it actually flips to the negative angles, which is fine. So that's sort of like what we were talking about last time a little bit. Okay. Now I want to show you what else you guys are working on. You guys are working on taking vectors, adding and subtracting them and stuff like that. Let's get rid of the values here for now, and I'll crack another vector over here. So there's another one I'll just change a little bit. And what you guys are doing when you're adding vectors and that type of stuff is, you take two vectors, you can put them together like this. That's really simple. There you go. That would be the answer. That would be the sum of the two vectors, something like this. And as you can see, if I make this vector bigger, then the answer gets bigger. And you can even do other things. For example, I could take this vector and I could turn it around. And if I turn it around, let's see if I can move that one around. There we go. I'll just offset it a little bit so you can see it. This one goes to the right. This one comes back to the left. And then the answer would be from the beginning to the end. It would be the result of those two vectors. Okay. And notice it doesn't actually matter where I actually place the vectors. Like I can put them something like this, where there's an origin, the answer didn't change. Now, that's one of the things about vectors, is you can move vectors, you can draw vectors any way you want, whatever makes sense. Different people do it different ways. Unless you actually change the value of the vectors, you won't change the answer. So how about if we take this, let's get rid of the answer, and let's do something similar to what you guys were doing before, where you guys were putting vectors together, and this was what we call the tip to tail method. So maybe somebody walked towards the right and they walked up. Well, the answer would be this, where it goes from beginning to end. And this is just one way to draw it. But what if instead I had the person walk up and then walk to the right? Notice that the answer didn't change. I didn't actually change the vectors, therefore the answer doesn't change. It doesn't make any difference. It's not until you actually change one of the vectors where the answer will actually change. It doesn't make any difference. Now again, this is like a tip-to-tail method of drawing vectors. I would recommend more drawing them. I always like to draw my x-axis vectors possible first, because it gives me a little x-axis to work with for measuring my angles, but it doesn't really matter. Now, this is a great way to draw vectors. Somebody's walking one place or another, but another way to draw vectors is what's called a free body diagram, which would be something like this, where that origin right there could represent like a box, or maybe two people are pulling on a box. One person's pulling up, one person's pulling to the right, and obviously the box moved to the upright in the resultant or sum vector. But notice it doesn't make any difference. Unless I change the vectors, it doesn't matter how I draw it. It doesn't make any difference at all. I could even do it with, let's get rid of the sum here, with three vectors. Okay, maybe I'll crack another one. There's another vector, maybe doing something like this or something like that. Okay, if I take these three vectors and I put them together, I'd like to start with my ones going flat. I find those the easiest. And then maybe this one, and then maybe something like this. And I crack out my answer, and my answer goes from beginning to end, just like you guys are doing. But what if I didn't start in this order? Well, it doesn't make any difference. I could start with that angled guy, and then I could maybe have the guy walk up, and then maybe he walked to the right. It doesn't make any difference. The answer is still going to go from beginning to end, okay, because I haven't changed the actual vectors. Now, what if instead of somebody walking around this represented like three people like pulling in a box, okay? Somebody's pulling to the right. Somebody's pulling straight up. Somebody's pulling down left. And that little origin there, that would represent my box or whatever they're all pulling on. Well, the box would have a total force doing something like this. Again, it hasn't changed because I didn't change the vectors. If I changed one of the vectors, now the actual answer will change. Okay, so unless you mess with the vectors individually, your answers won't matter. So some people, like when they do vectors, some people, here, let's get the answer vector out of the way. Some people like to always draw their vectors like this, which is a free body diagram. Some people always like to draw it tip to tail. It doesn't make any difference. I will actually flip-flop back and forth depending on the scenario. If it's something moving around, I like to use the tip to tail method like this. If it's things like pushing on a box or pulling on a box, like this would be three forces pushing on a box, where this is the box and I have the forces going in. Then I like to draw a free body, something like this. So it totally depends on the situation. Some people do always one way or the other way. Some people do a mixture. It doesn't make any difference because you'll end up with the same answer. Okay, so that's one of the nice things about vectors. You can sort of pick which way you actually prefer a lot of the time. All right. Now let me show you something else. When you guys were doing your vectors before and drawing them free body, you probably noticed that, since we're measuring with rulers and protractors, that answers can vary, and sometimes you don't want your answers to vary. Sometimes a general idea is fine, but sometimes you want exact answers, and you want precision and consistency, and everybody have the same thing. Now, this is where something else kicks in with vectors. This is where you have to start doing something else. So let's get rid of these guys, and something like that. Oops, get rid of that guy right there. Well, actually, no. Let's correct this guy. Maybe you walk towards the right or something like that, and then maybe you walk up something like this. And of course, the answer would be something like this, right? Well, there's no difference between walking to the right and walking straight up, or just going diagonally and just going across the sum or resultant vector. There's no difference between the two. So what if we actually reverse this a little bit? What if instead you walked directly? Now, if we do that, we can actually take this vector and angle, and we can actually break it apart and make it into a triangle. And notice that the parts of the triangle are actually the same as the two pieces we used to make it in the first place. Now, this is where some triangle math kicks in with vectors, where when we have a vector at an angle, like suppose it's not the answer vector, suppose it's the actual vector we're working with. Like suppose, you did something like this. Here, we'll get rid of that for now. Suppose we had this. Well, when we want to use this vector and actually work with it, what we often need to do is break it into pieces that look like this, because it's a lot easier to work with the sideways piece and the up and down piece than just the diagonal piece. And this is where some trig and Pythagoras kicks in, the triangle math kicks in, and we can actually take these vectors and break them apart into what are called components. We'd have the x component, which goes sideways. We'd have the y component, which goes up and down, and then we can actually work with them. And sometimes we only want to know how far sideways or up and down. We don't actually care about the other one. So this is where vectors by components kick in. So let me sort of show you how this type of thing works a little bit. So here we got a vector. We could break it apart something like this. Let's crack another vector, something like this. Okay. There we go, something like this. Or actually, let's swing that guy around. There we go, something like this. Okay, so suppose, we're going to get rid of the, okay, so let's suppose you walked something like this, and then you walked something like this. And the answer, of course, would be from beginning to end, something like that. Okay, now I'm just going to move that guy to the side a little bit over here. Now, what I could do is I could actually take each one of these things at an angle, and you can turn them into triangles, and they would look something like this. So I would start with this guy, and I turn into a right triangle, because right triangles are super easy to work with. So I could turn that into a right triangle. I would do the same thing for this guy. I would turn it into a right triangle. And then what I would do is I would take the sideways part from the first one and the sideways part from the second one, and I can put them together. And you can probably figure out, if I take the x component from the first one and the x component of the second one and add them up, they will be equal to the x component of my answer. So if the first vector went 5 to the right and the second vector went 2 to the right, then those two put together is 7 to the right. And what if, you could do the same thing with the y components. The two y components will add up to my answer y component. Okay, and that's literally how this type of thing works, where we take the triangles that we start with, we'll see how much they're going sideways, how much they're going up and down, we'll take all the sideways pieces, put them together, take all the up and down pieces and put them together. And sometimes they're not adding, sometimes we subtract. So for example, if the second one actually went to the left instead, well, instead of adding 2, now we'd subtract 2. And if I sort of bring this guy down, look at the x component, you can see that, you go to the right, how much of it is, and you go to the left, the overall result is what we're left with for the answer triangle. Okay, and that's sort of how it works. Okay, so this is the type of thing that we will get into, is we'll take vectors at angles that we can't really use easily, turn them into right triangles, take their pieces, and then recombine the pieces together to make answer triangles. Even if this guy, instead of going up, maybe it went down, well, same thing, We're still adding the sideways parts, we're still adding the x components because they're both going to the right, but then it goes up, and then the second one goes down, so we'd end up subtracting them to get the overall vertical part of my answer triangle. Okay, and this is what's called vectors by components. All right, and we can show other things as well. We can show angles and stuff that, and other things, and there's a whole bunch of values you can kick in. And this is, we'll get rid of the angle part, it's kind of messy, but you can sort of see how this thing kicks in. There we go. So for example, the first one here has got an x component of 11. The second vector had an x component of 7. We added the two together, which gives us the 18 for our answer triangle. Same thing for the vertical. The first one went up 7, the second one went up 4, so this one goes up 11. Okay, and if we went to the left instead, something like this, okay, the x component here is 11, the x component here is -5 because it's going to the left, so 11 take away 5 leaves us with the 6 on the answer triangle. And the vertical part, 7 as well as the 5, they still give us 12, they're both going up. So that's generally how this type of thing works, is we will take, we'll look at each vector, how far left and right, how far up and down, we sort of will organize them and make new triangles out of it. And that's the basic idea behind it. Okay, there's lots of other stuff, analysis that can kick in with this type of stuff, but that's the basic idea. And this is one of the top reasons you guys have been working on things like trigonometry and Pythagoras for years, especially trigonometry, because it really, really kicks in when you start doing vector analysis and that type of stuff. Okay, and that's the basic idea behind it. So what we'll do is we'll start working with vectors. Again, the best way to do it is just to jump into it and just start working with it. And once you get the hang of it, it's actually really, really simple. It doesn't really require anything past good old basic trigonometry. It works really well. Okay, but that's the basic idea behind it.